This is Daniel Coosbury, and in this video, I'm going to be introducing the idea of hypothesis testing. You have probably encountered at some point um, confidence intervals as a way of estimating parameters. The hypothesis test is a second way of doing that. So we're going to look kind of at the same situation where we have a population and we're interested in learning the mean. We don't know what that is. And if we don't have all the data from the population, we're never really going to know what the mean is. Like, we can't calculate this without all of the population information. And so what we'll end up doing is we'll end up taking a sample, and we can find the mean of that sample rather easily, and that mean can be big or small. And the big question is, how can we use this to estimate what mu is, or to confirm our suspicions about what mu might be? So you've had some exposure to confidence intervals, and confidence intervals uses the distribution of x bar to make what we would have an interval for mu. Hypothesis testing is a related thing, and I guess the difference is, instead of making an interval, we're going to make a claim about u. We're going to say, I think mu is this number, and we're going to see if our x bar is so far away from mu, what we think it is, that our hypothesis maybe isn't true. So for instance, let's just say mu is like 50. Let's just say that's our guess. And we take a mean, and we get a mean that ends up being like the number 5. Well, you could just look at that and say, well, if your sample's good and you get a 5, like, that's nowhere close to 50, like, this is probably wrong. But that's not a very sophisticated thing to say, like, this is just wrong because I think it's wrong. We're going to use the probability theory, the central limit theorem, and statistical methods to say, okay, well, if this is really true, how likely is it if this is 50? So we'll kind of work through that. Keep in mind that this whole idea of probability comes from the fact that if I was to take a sample and get a mean, that sample mean's not guaranteed to be any one number. Like, I can go in and get another sample and get another sample mean, and maybe that's x bar 2. And like, I have no reason to expect these two things to be the same. In fact, if they were, it'd be amazing. But these are random things. So we're going to talk about probability and likelihood of, like, how likely is it if this is 50 that I get x bar to be maybe 53, as big as 53 or something like that. If this is true, how likely is this? Or if this is true, how likely is it that I get x bar is equal to 57 over here? Because if this is unlikely, maybe this isn't true. Maybe my hypothesis is wrong. So we're going to start by making hypotheses, and we're going to test whether they're good hypotheses or not. And the good thing is, regardless of whether our hypotheses are good, we'll have a lot of information that we can share as a result of our test. Now, let me kind of warn you that this video is not designed to show you really how to do a traditional hypothesis test. These steps are not in any real textbook. This is just the idea behind it. So this is my best stab at introducing hypothesis testing, especially if you've never seen it before. In later videos, I'm going to give you definitions and nuts and bolts and like pieces of them, and I'll give you some examples how to do it properly. This is just the general idea. So just follow along with me for a few minutes, and then later videos will have the actual, like, what I would expect you to do on a problem. So let's start with this idea of making a hypothesis about mu. So we got some population mean, we don't know what it is, and we're going to make a hypothesis that mu is equal to 30. We have good reason to think the population mean is 30. And let's just say that we know that the standard deviation is 10. Like, maybe that's just something we know already. And we don't know mu, so we're just going to say this is 30. So this is our hypothesis, is mu is equal to 30. This whole statement right here is the hypothesis. Now let's say that we take a sample of size 50, so there's our n, from the population, and that sample has a mean of 33. Okay, so think back to that little box picture. So I'm thinking mu is 30, but I take a sample, and x bar is equal to 33, and so this is my hypothesis, and this is what I get from a sample. And then we're going to ask the question when we take a hypothesis test: if our hypothesis is true, so if mu is really 30, how unusual is it that we draw a sample of 50 things that has a sample mean as extreme as, that word should be there, as extreme as x bar is equal to 33. In other words, if this is true, how likely is it, or how strange is it that we get a mean that's bigger than it, even by 3 units? Okay. Now, some things that I'll point out in a later video is there's this word unusual again. Like, what does this mean? Sometimes we call unusual. If it's less than 5%, we'll say it's unusual. Sometimes this number changes. So this is a general word that is going to change. We're going to decide what unusual means. And then extreme is another word that might change. So for instance, when we say extreme, we might mean as large as. So for instance, how likely is it I get a mean as big as or bigger than 33? I might, in a different case, I might say something is as small as, and then there'd be a number smaller than 30. So if I had x bar is equal to 20, 24 or something in a different example, I might say as small as, not as extreme, or not as large as, but something as small as. And then extreme is general because sometimes when we use the word extreme, we might mean both. So like, what's the chances I get something 3 units bigger or 3 units smaller than 30? Like, what if I wanted something like, what's the chances I get something as low as 27 or as high as 33? So that's kind of what, this thing's going to change a little bit in different problems too. So these are just general words. We'll put some skin on them in a more specific video. Okay, so the context is I'm guessing my hypothesis is mu is 30. I'm asking the question, how unusual is it that we draw a sample of 50 items that has a mean at least as extreme as x is equal to 33? And in this case, let's just say this means at least as large. So something that's at least 33 or bigger. And this is something I know from the problem. This is where the central limit theorem comes into play. So according to the central limit theorem, since n is large, it's bigger than 30, x bar is normally distributed with the mean is equal to mu, and the standard deviation of x bar is equal to sigma over square root of n, which it turns out to be this number. So this is something you've worked with before. Regardless of whether this is true, I know that x bar has this distribution. It's normal. It looks like a bell. The mean is 30. There's mu. The standard deviation is 1.41. So there's mu plus 1.41. There's mu minus 1.41, and so on. So I know this distribution is true. Now, based on how we define words like extreme and unusual, we can decide if the hypothesis is worth considering, or we can decide that it's probably not true. So this or kind of, and again, this is not how I would answer questions, but this is kind of the goal is we want to know, is this a valid hypothesis or is it not true? Okay, so this is the distribution of x bar. X bar is normal with mean equal to 30 and standard deviation equal to 1.41. So I'm sorry if that's backwards, 1.41. So you see this is the distribution of x bar. Now I guess the way you should look at this bell curve is if I get something like here, you know, like the bell curve, like 68% of the distributions between these two things, like if I were to get 29, like that's a really common thing to get, assuming if I were to get I'm assuming mu is 30, by the way. If mu is really 30, then if I get 29, that's common. If I get 31, that's common. If I were to get 25, like over here, that would be very uncommon. There's almost no area there. The probability of getting that is very, very small. So here's the thing. If mu is 30, I drew a sample whose mean is 33, so it's up here. And I want to answer the question, if all of this is true, if this is true, this is true. If this is true, what's the probability that I draw a 33 or bigger, something at least as big as 33, 33 or bigger, at least as big. Those mean the same thing. In other words, I want to find this area right here. This will tell me the probability if mu is 30 that I get something 33 or bigger. This is something we'll call in a later video a p-value, this area right here. It's the chance that if the hypothesis is true, I get a mean at least as big as that, if not bigger. So I can find this because I know the distribution. This is normal. There's the mean. There's the standard deviation. So I could use normal CDF if I wanted to. Again, this is not how I would do it in a hypothesis testing problem. There's a little more precise method. Precise is the wrong word. There's a more standardized method that does a little different than I would. But let's decide that extreme means X bar is 33 or larger. So we're looking at this sliver right here. This is what we mean by at least as extreme. Unusual means that if this probability, if this red sliver, so this is the probability that X bar is bigger than 33. If this probability is less than 5%, we're going to call it unusual. So that's like a typical meaning of unusual. If this sliver is less than 5%, the chances we get something 33 or bigger is less than 5%, less than 0.05. We're going to call it unusual. And if it's unusual, there's something wrong with our assumption that mu is equal to 30. I know I'm saying a lot. I'm trying to introduce an idea. Trust me, you're going to need to watch a few more videos to really get a feel for what's going on here. So in this example, I know that X bar is normal with mean equal to 30 and standard deviation equal to 1.41. So I can find this probability by doing normal CDF, going from 33 all the way to infinity, and then putting in mean of 30 and standard deviation of 1.41. I did that backwards again. This is 1.41. So I could do like normal CDF, go from 33 to 999, 30, and 1.41. And I get the probability that. So this area is equal to 0.0167. So this is the chance that if my hypothesis is true, the chance of getting a 33 or bigger as a sample mean is almost it's almost 1%. It's 1.67%. Pretty small. The point now, our takeaway is going to be that since this is smaller than what we defined unusual to be, so unusual is 5%, this is 1.67%. Since this is smaller than what we defined unusual to be, then we can say, okay, well, maybe there's something wrong with our hypothesis. We don't want something unusual. If this is true, this is unusual. So we can say something now. Okay, so here it is again. So the probability that X is at least as big as 33, X bar is at least as big as 33 is 0.0167, which is less than 0.05, which is our unusual. So if our hypothesis is true, it would be unusual to get a sample size at least as big as this. So this is how hypothesis testing works. We're going to conclude that our hypothesis is probably wrong. We're going to conclude that this hypothesis is probably wrong because getting a mean this big is strange. So there's something wrong. So what we're going to conclude is that our mean is actually bigger than 30, and that's about all we can say. So the goal of the hypothesis test is to either say, well, I have no reason to believe this isn't true. That's flaky statistical language. I have no reason to believe this is not true. It could be true. Or we would disprove it and say something like this. Okay, well, according to my evidence, this is big enough, so much bigger than 30, given all my data and the probability and all that, that my mean is probably bigger than 30. My true mean probably is bigger. So that's the whole idea of a hypothesis test, is to either say, well, this could be fine, or to say, this is wrong, and let's say something like this instead. It's bigger than 30. I can't say anything more specific than that. So this is my introductory video. I don't expect all this to make sense right away. So work through some textbook things, look through some further videos. Learning how to do a hypothesis test takes you got to learn a lot of definitions, a lot of steps, and we'll eventually get there. So yeah, good luck.